Hello everyone, this is SAVITHA Acharya from Canara Engineering College. In this video lecture, we will deal with the more examples in gate level modeling. 4-bit full adder is the next example. Here I have the block diagram of the 4-bit full adder. The name I have given as FA4, and 4-bit full adder is a circuit that adds two numbers each which are 4-bit wide each. Okay, so it will have two numbers 4-bit each, so that I have given as A and B. So the way in which we write vectors in the block diagram is, you just have to write the input arrow indicating it's an input line, and A and B. So these are the signal names, and to indicate that it is not a single line but multiple lines, we write a slash over that arrow and write the number of lines that it is representing. Okay, so it's a 4-bit number, so I write /4. So this will be, depending on how I declare the vector in my program, it will be having index values, say A of 0, A of 1, A of 2 and A of 3 and so on. And in addition to these two inputs, there will be one input that is single bit input, that is input carry. I have named it as C underscore in, and there are two outputs. Again, sum is again 4-bit corresponding to the two input numbers, 4-bit two input numbers, and output carry, that is single bit. Okay, once you have the block diagram clearly labeled, you should be able to write the module definition. So module definition is module keyword followed by FA4, and inside the brackets the port list. So port list is A, B, C underscore in, sum, C underscore out. This is the output carry. Okay. Next is declaration of input and output. So input A and B are the inputs, but this A and B, if you just declare it as input A, B, they will be declared as single bit lines. Now that we know that A and B are not single bit lines, they are 4-bit lines, that is, it's a 4-bit vector. So I declare it as, in square brackets, 3 down to 0 A, B, meaning A and B both will be declared as 4-bit vectors. The other input is, as you know, the single bit line, that is input carry. Next is output. Again, sum is also 4-bit line, that is 3 down to 0 sum, and the output carry is single bit line. Okay, this is done with the module definition. Now next comes the implementation. So a 4-bit full adder is implemented using 4 single bit adders. Okay, the name of the module is full adder, FULLADDER. Okay, so we require 4 full adders, 4 1-bit full adders to realize a 4-bit full adder. Okay, 4-bit adder. So the full adder, again, it adds two numbers which are single bit, and in addition to that it takes care of the input carry. Output will be one sum bit and other bit is the output carry. So what I do is, I take the corresponding bits of A and B and feed it to the 1-bit full adder to get the corresponding sum and the output carry. So the 4 full adders are cascaded. The output carry of the first full adder is taken as input carry of the next full adder, and so on. So output carry of the last full adder will be the final carry out. Okay, so this thing you can see, that is the interconnection. A of 0, first full adder FA0, it is input is A of 0, B of 0, and carry in the Cin port, Cin itself is fed to the first full adder. Okay, output of that will be sum of 0 and carry out will be taken as some intermediate signal C1 and that will be fed to the next full adder as input carry. So C1 becomes the input carry to FA1. FA1 is the second full adder in the series. Okay, so that is going to add the second bit of the two numbers, that is A of 1 and B of 1. So output will be sum of 1 and C2, that will be the carry out. Okay, so similarly the third full adder will get C input carry as from previous one, that is C2. It adds A of 2 and B of 2 and gives out sum of 2 and output carry C3, which will be taken as input carry to the last full adder. So this adds A of 3 and B of 3 and output will be sum of 3 and the carry out of this stage will be the final carry, that is C out. Okay, so you don't have to bother much here in gate level modeling. You just need to have the detailed logic diagram with appropriate labeling. Okay, so now I need to instantiate 4 full adders. Okay, and as per this, so all these A's and B's are ports which are already declared. C in is declared, C out is declared, sum is declared. Only thing that are not declared are C1, C2 and C3. These are intermediate signals. See, always we write the intermediate signals internal to the outer box. See here, we have you can notice this dashed line, a box with the dashed line, and the outside this dashed line, whatever terminals you see, these are the ports. May it be input or output ports. Whatever is inside that, whatever is named inside that dashed box are the internal signals. So those you need to declare as, say, wire C1, C2 and C3. Okay. So this is done with the intermediate signal declaration. Now I need to instantiate these full adders. So I will give the name of the module. So this is full adder. FA0 is the name of the instance name or instance label. Okay, and I need to map the ports. So I will give A of 0 first, B of 0 next. These are the two inputs to the first full adder FA0. Carry in is C underscore in, that is the input carry, and output of this is sum of 0. The sum bit is sum of 0. And carry out is C1, the intermediate signal that you have just declared. Okay, so this is the C1. Now I have done this, I have put this order assuming that when I am writing the program for the full adder, this is the which I have not yet shown you, this will be the order. Okay, that we'll see later. Now I need to have 4 component instantiation lines for 4 full adders. So I have written the remaining instantiation lines. FA1 is A of 1, B of 1, C1 is the input carry, sum 1 and C2 is the output carry. FA2 is A2, B2, C2, sum 2 and C3. Okay, and FA3 is A of 3, B of 3, C3, sum of 3 and C out. Okay, so you just have to write the detailed logic diagram appropriately labeled and directly its textual representation you have to simply transfer. Okay, in the Verilog code. So next is you have to now describe or the full adder. Okay, so initially in gate level modeling, if you see the previous examples that we have seen, we just use the primitive gates. We just instantiate the primitive gates. Primitive gates are the ones which are predefined in Verilog, like and, or, not, nor, NAND, all these things. Okay, but now I have used full adder as a component to realize 4-bit full adder. Okay, but this full adder is not predefined in Verilog. So you have to define what is a full adder. So this program is not complete. We'll continue this. We'll have to continue by writing the full adder program. Our next job is to describe the full adder. Now we have realized the 4-bit full adder using 4 full adders. So as I've told you, full adder is not predefined in Verilog. So you need to describe what is a full adder. So I've put the block diagram of the full adder. A, B, C are the inputs, sum and carry out, C out are the outputs. So with this I should be able to write the module definition of full adder. The name of the full adder is module name is full adder, and the inputs are A, B, C in, sum. See, the names that I have given here has nothing to do with the names that I have given in the 4-bit full adder. Okay, so this is modular programming. So the outputs, inputs, port names are not going to interfere with the other modules. So input is A, comma, B, comma, C in. So note here all these are single bit lines. So in the 4-bit full adder, we declared them as A and B as 4-bit vectors. Okay. Now we are describing a full adder which is going to add only 1 bit. So all these are single bit lines. Now the implementation of the full adder. So note here we have implemented the full adder using 2 half adders. Okay, this one is one half adder, that is XOR gate and AND gate is a half adder which is adding A and B, and this XOR gate and AND gate is another half adder which is going to add the sum of A and B and C in, input carry. Okay, and the carry out is realized by ORing the carry out of 2 full adder, sorry, 2 half adders which are cascaded. So this is the full adder implementation using 2 half adders. So I will just write whatever is implemented here textually. So now the first instantiation, let me take the first OR gate. That say here instantiations are, there are 2 XOR gates, 2 AND gates and 1 OR gate. All are 2 input gates. Okay. So XOR, one first XOR gate is say A1, and I have one more XOR gate, that is A2. Okay. So now first we'll write what is the expression, what are the port list for the first OR gate, that is A1. So to A1 input is A and B and output is S1. So I think we missed out writing the declaring the internal intermediate signals. There are a few intermediate signals. So as I've told you, whatever is internal to this dashed box are internal signals. Okay. Outside this dash box are the ports. So the internal signals are S1, C1 and S2, right? So I need to declare them as wire, say wire S1, S2 and C1. So it is S1, C1, S1, C1 and C2. Okay. So now the component instantiation, the OR gate A1, output is S1 and input is A and B. So as you know, the primitive gates syntax goes by this, that is the terminal list always first one should be the output followed by the inputs. Okay. So this is the first XOR gate. Now the second XOR gate, that is A2, the output is sum. The output is output port sum and input is S1 and C in. Okay. So sum S1 and C underscore in. Next is there are two AND gates, A2 and A4. Sorry, the XOR gate is, the first one is A1 and as per the label I have given, it is second XOR gate is A3. Okay. The AND gate, there are two AND gates. The first AND gate is A2 and the next AND gate is A4. Okay. So now, how do we instantiate the ports here? The A2 output is C1, A2 output is C1 and input is A and B. C1, A, comma, B. And A4 output is C2, input is S1 and C in. Okay. A4 input is S1 and another input is C in, output is C2. So C2 S1 comma C in. Okay. Now the last instantiation is OR gate. So OR is the primitive gate. The instance label is A5 and ports are, the output port is the output terminal is the output port C out, C underscore out, and the two inputs are C1 comma C2. So this is the OR gate. Then end it with end module. So this is your representation of the full ladder. Okay. So full ladder also I have described using gate level modeling. We'll move on to write the test bench for this 4-bit full ladder. Now for your reference, I have put the block diagram of the 4-bit full ladder as well as the full ladder, 1-bit full ladder. Now understand that we are designing or realizing the circuit for 4-bit full ladder. So your 4-bit full ladder is the top level module. Okay. In this 4-bit full ladder, I am instantiating a 1-bit full ladder as a component. Please understand this. Okay. So this 1-bit full ladder is a component to realize this 4-bit full ladder, and I have used 4 instances of this 1-bit full ladder to realize or implement this 4-bit full ladder. Okay. So now my top level design is the 4-bit full ladder and I need to write the test bench for the 4-bit full ladder. So this is internal to your top level module. This is a component. So don't confuse. That's why deliberately I have given the port names same. Okay. So it is simply modular programming. It is not going to interfere with each other. Okay. So this is your top level module. I'll be writing the test bench for this top level module, that is the 4-bit full ladder. So the test bench will continue like this. say module is the name of the module keyword. The name of the module I will take it as FA4 test bench, indicating that I am writing test bench for the 4-bit full adder, and there is no port list, that's why empty parenthesis and a semicolon. Now, what are the inputs and outputs I require to apply the stimulus for this 4-bit full adder? The 4-bit full adder has got two inputs which are 4-bit wide. Okay, so this should be declared as a register, and they have to be compatible. So it is 3 down to 0, say x comma y. I will simply give some other names. So two inputs which are 4-bit wide, and one input which is the input carry. I will take it as C, and the output is wire, which is which is a sum, 4-bit sum. So I will take it as S, and say one more single bit wire, that is C out. Okay, I will take it as a CO for C out. Next is I need to instantiate this 4-bit full adder inside this test bench. So the name of the module is FA4. I'll give some module instance name, and so the port names which I am going to map with the actual module should be compatible. So here in the test bench program I have given some other names, but they should be compatible. In my 4-bit full adder, if you recall, first one is A, which is a 4-bit number. Second is also B, which is a 4-bit number. So here they correspond to X and Y. Third one is the input carry, which is named as C here. Fourth parameter was in my module definition for 4-bit full adder. Fourth parameter was sum. Here I have declared it as S, which is a 4-bit number, a 4-bit signal. And the last one is carry out, that is single bit line. Now this is the instantiation of your 4-bit full adder inside the test bench. Okay, so now I need to give the stimulus to the input, so that should be done inside the initial block. So initial syntax is initial, then whatever statements you need to write should be inside begin and end. Now what I will do is I will give some random numbers, because here 4-bit if I go by the conventional rule of giving all possible values, all possible test vectors, then see the input is one input is 4-bit, so in that I can have 16 possible combinations. Another input is 4-bit, again 16 possible combinations, and one more input, that is input carry. So 4 plus 4 plus 1 is 9. So if I go by that conventional rule of applying all possible combinations for the test vectors, then I need to give 2 power 9 combinations. So my test vector length would be very large, 512. So here what I do is for my reference, for my functional verification, I'll give some random numbers. Okay, so I will give say X as some 4-bit number, say 5. So how do I give the 4-bit number? It is better for me if I give in decimal. So decimal digits, a 4-bit number, the number of bits is 4. Tick D indicates that the value that is going to follow is a decimal number. So I give it as 5. This is first number, and second number I will give as say 9. 4 tick D 9, and input carry, which is given as C here, I will give it as 1 tick B 1. Okay, so input carry is 1. So first number is 5, second number is 9, and input carry I have given as 1. Likewise, I can give some other set of numbers randomly. I give some values. Say I'll give some delay first here, say #10. That means after 10 time units, let x be say 8 and this thing be say 6 and input carry let me give for a change as 0. So like this random some 4 combinations, random 4 this thing you give and finish off with the test bench. So I have given some more random numbers, say x equal to 3, y equal to 7 and carry is 1. Likewise 4, 3 and carry is 0 for every 10 time units. Okay. So note that again I repeat, this full adder, 1-bit full adder is a input internal component that you are going to use to implement this 4-bit full adder. So always we will be writing the test bench for the top level module. Okay, if you remember now this is the waveform of the 4-bit full adder test bench that we have written. So this is x that is 4-bit number and y 4-bit number. So as I have told you before, the 4-bit or multiple bit signals are represented as parallel lines. Okay, and whenever there is a change in the value, it is shown by a crossover. So here for this duration the value of x is 101. And at 10 time units it becomes 1000. So to show the change in value, the crossover, the two parallel lines are crossed over here, and again they continue to be in the continue to be as two parallel lines. C is input carry, that is 1-bit signal. S is again 4-bit signal, same convention used, that is two parallel lines and crossover whenever the signal value changes. And CO is the carry out of the 4-bit full adder, that is also a single line. So initially in the test bench I have given for at time t equal to 0, I gave x as a 5 and that is 101 in binary, and y as 9, that is 1001, and carry in, that is C, I have given as 1. So 5 plus 9, 14 plus 1 is 15. So this is binary 15, 1111, carry out is 0. After 10 time units, I gave x as 8 and y as 6. So 1000 and 0110. Carry in C is 0. So 8 plus 6, 14 plus 0. So output is 14. Sum is 14, 1110, and carry out is 0. Next, after another 10 time units, that is at 20, in x we changed it to 3 and y as 7 and carry out is 1. So 3 plus 7, 10 plus 1 is 11, 1011 is the sum, carry out is 0. So after another 10 time units, x is 4 and y is 3, carry in is 0, so output sum is 7, carry out is 0. After that I have not changed any test vectors, that's why it remains in its latest value. Okay, this is the waveform of the 4-bit full adder. Now remember that for different designs that we have realized, the application of test vectors is different. That is, the way in which you give test vectors is different. You have to understand what is the input and what values what input we need to give in order to verify the functionality of the design. Okay. Now, as I've told you, for a 4-bit full adder, it is not possible to give all possible test vectors. That is 2 power 9 combinations. That's why here we have taken randomly randomly two different values for x and y and verified the functionality. Okay. So depending on it on the design specific circuit, the input test vectors have to be applied. In this video, I have dealt with the 4-bit 4:1 multiplexer and 4-bit full adder using gate level modeling. In the coming video, we will look into various delay examples. Okay, thank you.